Hello, sir. Am I audible? Sir, am I audible?
Hello? Hello? Don't think. Hello?
Yes, sir. Now I can hear you.
Now I'm audible? I guess
Yes, yes, yes. I can hear you.
for some reason. Hello? I'm still audible? Let me start because I have only. Yeah. So thanks for showing up because it's a special class that you didn't have to. Sudakshina, you can still hear me?
Yes, I can hear you.
Okay. Yeah, I think it's working. So she spoke and it is still. Okay, just to set the context, remember that what we were, yeah, seeing that, okay, one of the reasons why SAT solvers, one, one of the bottlenecks of the DPLL method is that as a result of making some wrong decisions, these are decision literals. Whenever you make a set of wrong decisions, you will get a conflict because the decisions are inconsistent with your original set of clauses. Okay, and sometimes, and then so because the DPLL just keeps trying. Okay, it backtracks to the latest one, and it tries to exhaust all possible decisions up that you made up to that point before backing up. So you could end up maybe okay, you could end up hitting the same conflict like as it happens here. The reason that this conflict here is arising is because once you make a decision on X1 to be true, X4 has to be cannot be one. Okay, and the all the decisions that you end up making after that happens to imply infer X4, forces the implied decision on X4 to be one, and that can happen due to various reasons depending upon what your clause structure is. So that's what is happening here. Okay, now you could, by luck, if you had made some of the set of decisions well, which did not imply X4 to be one, you could have probably got some satisfying solutions, but bad luck have it, you could end up having these kinds of things depending upon the decisions that you make. So one significant improvement one significant breakthrough that led to a significant orders of magnitude improvement in the performance of SAT solvers was to Um, Oh, it is working. Okay. So was to, and as I said, this is because the original set of clauses imply something, that if you knew, if you could have inferred this before you made the decisions and then had that as part of your database, then, perhaps you could prevent that. And that's the first thing. So first improvement is whenever you hit a conflict, you try to you'll analyze that conflict and try to learn something from the conflict. You learn actually a clause, okay, which is a consequence, which is actually implied by the original set of clauses, and you can then you can add that clause. In this case, this can prevent that conflict. Once you add that conflict, this particular conflict clause, so that is what is called conflict-driven clausal learning, because you're learning this clause, which is an implied clause, as a result of these the conflict. Okay, so that is one. So, and the idea there is once you learn the conflict, you add it. You can always add it because this is implied by the original set of clauses. Okay, and once you add it, what happens is, as soon as you add, you see, because X1, you have already made a decision, you would have backtracked to X7 here, for example. And then before you flip the decision, you will already, since X1 is 1, this will immediately reduce to a unit clause and forces an implied decision of X4 to be 0. Okay, and therefore you certainly will not hit these repeated conflicts. Okay, and as I said, the other improvement is if you are learning such clauses, why only backtrack to the latest level? You could skip. You could do, yeah, okay, so what was the thing? So how to, so the thing that we will see today is how to learn these clauses, or is this the only way to prevent that? There could be several ways. I mean, you could, to prevent that. You should learn something such that when added, it will prevent this conflict from recurring in future. Can there be multiple conflict clauses? And if there are, which one you will all add? So by a conflict clause, what I mean is that it is a clause which is implied by the original formula and is such that it can block the conflict that that you had, okay, from recurring. Okay, that's how you define a conflict clause. Okay, the other one is, as I said, that you could do non-chronological backtracking. If so, then which
Why X7 is not added?
Hello?
So why X7 is not added?
Why? Can you repeat that?
X7.
Dakshana, is the question for me?
Yeah, it is a question. That is why X7 is not added.
You get it?
X7.
Why X7 is not added to what?
To the CC1.
Or to CC1. Why would you want? Okay, no. Of course, there is a, you could have, no. So this is certainly, you don't need to add X7 here, because as a result of X7 being 0, okay, that implied, okay, as you can see, so in this whole sequence of things, okay, as a result of X7 being 0, it started a chain of BCP propagation, which implied, okay, x4 to be 1. Therefore, it is enough if you add this to prevent that particular conflict. Okay, like I said, you could prevent it in other ways as well. One thing is, of course, you could say, you cannot be making the decision, all the decision literals, explicit decision that you made, Sudakshina, you could do that. So then, so for example, x1 being 1, x8 being the negation of x1 being 1, x8 being 1, and x7 being 0, that the negation of that set of series of decisions is also a conflict clause, because you could say that that is the cause of the thing. But here you don't need x7 because anything about a decision on x7, because that is what led that implied x4. Okay, therefore this is actually one of the shortest clauses that can prevent from inferring x4 to be 1 once an decision x1 is made, because you don't need x7, because the moment you have x1, it'll actually force x4 to be 0, and therefore, regardless of what decision you make on x7, you get the right decision on. You will never be allowed in that case to make this wrong decision on x7. So therefore, in order to avoid this conflict, this is the root cause of the conflict. Any set of decisions that would make you imply x4 to be 1, x1 and x4 both to be 1. Any such is also a possible conflict clause. Okay, and that shows that there are many ways in which you can prevent it. But for this particular thing, you don't need. If you added this, you don't need x7. Okay, anything to be part of x7. Okay, so that's what. Yeah. So the question is, how do we? What we'll be looking today is how we derive that. And you will see, Sudakshina, that there are conflict clauses, which block that conflict, which have x7 as a part of it as well. Now, before I do that, I want to, because resolution.
So these are a disjunction, right? This classes.
Say that again.
The class, all classes are disjunction, right?
Yeah. It's the conflict clause is a disjunction. Yes, it's a clause, correct?
No, this all plus is they are all disjunction, right? Plus x1 bar plus x2.
Is or. Yeah. I'm sorry. Yes, I interchangeably I use plus and or symbol interchangeably. Yes. Okay. So. And resolution, as you'll see, will play an important role. So I just want to make a couple of observations on the rule that okay, no, this one. Okay. So you recall this. Now, see, when you apply a resolution, okay, so this was, so I said equisat. Okay, another, a more direct way of saying what a relationship between resolvent and the original set of clauses is, the resolvent is actually implied by the conjunction of the original two clauses. That is, C1 and C2 always implies R. Okay, but it's not true the other way around. Okay, it's not necessarily true the other way around. Okay, so resolvent need not imply C1 and C1 and C2, because there is a way to make this to be true. Okay, yet you can pick this conflicting value for the conflicting clause in a way that makes this C1 and C2 false, and that's why the reverse is not true. Okay. The other thing is, you see that because this implication holds good, actually not of R implies not of this. Okay, which means anything, any negation, when you take the negation of this, it becomes a cube. Okay, it determines a particular assignment to the set of literals listed here. If you plug that in, then that will make obviously C1 and C2 to be false. Okay, in particular, the assignment, which is represented by the negation of this, will make each of this two clauses to be unit. Okay, and then it'll be in C, there will be conflicting. This will make C to be 1, and this the assignment will make C bar to be false. Okay, so you observe that. Okay, and then we'll be using that in this observation to derive conflicts. Is that clear? For example, in here, if you have this A or B or C, and these are the two things, the resolvent is this, correct? When you resolve, yeah, A or B or F, if you take the negation of this, that will be not A, not B, and F. A and B get 0. So when you plug that, A and B to be 0, this becomes C, and F being 1, okay, will make, and B being 0 will make C bar, okay, to be 0. So which means that this one of them will become a unit, and they'll conflict. Okay. So is that clear? Yeah. Okay. So just keep that okay in mind, and we will see. So then I'll get back to that. So what do I want to do? Okay. So, and now since we have seen resolution graphs, now this BCP, which moment you make a set of decisions, what happens? What I'm showing here is this Boolean constraint propagation, BCP. That can also be, obviously, it can be, let me get to that, okay, can be described by means of a resolution graph, okay. And that's what I have here. Okay, so here, see that particular series of decisions that you made, you started with X1 being 1, then X8 being 1, and X7 being a 0. So if you added these unit decision literals, and they conflicted with the original set of clauses, which was C1, C2, C3. So whenever a set of a set of clauses, a set of clauses is conflicting, resolution principle, I mean, you should be able to derive a conflict, okay? And that you could derive using a series of application of resolution rules, correct? And that's what this thing is saying. So for every conflict, once you make a set of decisions, okay, if you want to look at what happens, if you want to see what BCP, the Boolean constraint propagation, see, in a very informal way, Boolean constraint propagation is nothing but you just plug whatever the decision that you have made, and then you simplify it, okay? That is the easiest way to do. Now, there is value in seeing it as a series of unit resolution as well, and that's what I'm describing here. This is just for your theoretical understanding that there is always a resolution way of showing this. So because, yeah, so you can add these decisions as addition if you add them as unit clauses, okay? And then there will be a resolution proof that shows of a deriving conflict, correct? Okay. So now basically we will be analyzing, if not this, essentially a resolution proof of that in order to derive the conflict clause, okay? But rather than using this, we use a decluttered version of this resolution proof, okay? So here in a resolution, in the traditional resolution graph, you have all these intermediate steps, okay? Where you, in order to get this unit literals, in this case, there was a unit literal by just plugging this thing in. But sometimes you will have to do a whole series of plugging in before you get a unit clause, okay, to further trigger this BCP propagation. So what you really, it turns out that you need to maintain is the kind of just the dependency, how you, the series of what led to producing each of these implied decisions. So the same thing can be, this is your original graph. This can be decluttered by getting rid of these intermediate, by keeping only the unit clauses that got resulted as a result of making these unit decisions, okay? And the clauses in which resulted in those, in producing those unit literals. Now, for example, here, so when you made this decision X7 bar to be 1, that obviously, when you plugged it in C5, it resulted in a unit by X5. And that's what this thing is saying, is X5 bar, okay? So it is keeping track of how this unit literal was implied by the BCP at that, in that step, okay? So, similarly, X6 was produced by what is this? C5, okay? C5 and C6, correct? Okay, because this itself was produced, X5 bar was produced by XC5, and then, so, and therefore this was produced by these decisions and these two clauses, and that's what this thing is keeping, okay? It is, I say it's decluttered in the sense these non-unit resolvents are all removed there, but the dependency of each implied, so usually these decisions are called decision literals, and these are implied decisions, okay? Things that are implied by BCP at level, BCP happening at level 3, okay? So, and this is the kind of, this is what is called an implication graph, okay? Because it precisely shows the all the implied decisions by the BCP and its dependency on the explicit decision that were made and the clauses in which resulted in when those decisions, explicit decisions were plugged in, implied these literals. And you'll see that all the conflict clauses that can block this particular conflict can in some way derived by analyzing this implication graph, which itself has enough information as same information as the resolution graph. And we'll see that. So, okay, so I'm going to switch over to another set of slides where that's this one. Okay, so before I go there. Okay. So this is just, let me go back. Yeah, that's what I'm going to show you. That's here. Yeah. Okay. So both these pictures are from chapter 2. Okay. This is just a pseudo code version of this flowchart. Okay. So we'll actually be using this pseudo code, okay, when we trace the implication graph and so on. So as you can see, this you start with. So you do this is the original formula, and this is the set of assignments that you have. And initially you do a BCP with empty assignments. Okay. And if so, then you can get out immediately if you get a conflict. Otherwise, you have to repeat this loop, okay, until there are no unassigned variables. So you have to keep making decisions as per some heuristic decide, and then you do a BCP. And as long as doing the BCP does not give you a conflict, you keep going, okay? Adding newer and newer assignments, at increasing, by increasing the levels. The moment you get a conflict, then you will analyze the conflict. As a result of analyzing that conflict, you will get a conflict clause. How we generate it, which ones you pick, that's what we will see, okay? We're going to dive one level deeper into analyze conflict, and that's what I will be doing now, okay? And in addition to that, adding that, you then it also gives the backtrack level to which you have to, it says you have to backtrack. These are the two things that analyze conflict will give, and then you backtrack to that, and then you keep doing it until you either get a conflict, okay, after backtracking to level 0, or you will get at some level a satisfying instance, okay? So that's, I wanted to show. So that's the thing that I will be using. So now let me get back to this one, okay? So I'm going to go through this quickly. Yeah, so this is a repeat of what I had already shown you. Therefore, I'm going to go fast. Okay, this only thing it shows is, it shows the construction of the implication graph. As you, go through this, this code, okay? So first you make this, and then you do BCP. Every time you make a decision, you have to do a BCP, okay? So there's nothing, so it does not simplify it any further. So, you make an explicit decision on X8, okay? And then still there are no unit clauses. BCP does not produce anything. So this is X7, okay, being 0, okay? So that's the series of decisions. Then, yeah, at this should be at 2, okay? Why? That's the level. So you start with 1, then at 2, and then at 3, okay? So if there is a, the implication graph is usually called a partial implication graph for the reason that it only analyzes, it shows the how a conflict was arrived at, how a conflict, ended up being produced as a result of some set of decisions that were made at earlier levels, along with a latest decision that has been made. Okay, and so in this case, that latest level is at 3. Okay, and that's what is happening. So that's how you can generate. In this case, you can directly plug that these decisions into it, and then do it. So that this resulted in this decision, implied decision, and similarly, you got X6, and those two then further, when they got plugged into C4, it gave rise to X4 to be 1. Okay, and I think, sorry, so you guys should, yeah, I think if I make it bigger, I mean, full view, it will be better. Yeah, okay, I think it's better now. Yeah, so. Okay, so then you keep going. So this in C3, so that was resulted in X3 and so on. So then you got the yeah, X1 decision and the moment X4. So C1 also became unit to X2. And finally, these things, when you got plugged into the clause C2, you got a conflict. Okay. Now, a couple of observations. One is an implication graph. There can be so many different ways in which you could have arrived at a conflict, okay? Even with the same set of decisions, because it very much depends on which clause you choose among the ones there to plug your decision first, okay? And that itself will determine. So the order in which you choose the clause. So therefore, and the same, you know, the conflict you could be producing depending upon which clauses you choose to plug. The eventual clause in which reduces to false, which is what is producing, could be different. Okay, so there is no. You can have multiple different, distinct implication graphs explaining the same conflict that results as a result of these decision literals that were made. Okay, that is one. So that is one that you will have to you know, observe. And what is it that? Yeah. Okay. So then, how? The question is, how do you get this conflict clause? Okay. So let's see. Okay. One is these things I've already gone through. Yes, some definition. So an implication graph, the nodes of the implication graph are all implied. The nodes are either explicit in a decision that were made at the current level or a level, and all the other ones are the internal nodes are all, if not the conflict node, is something that was implied by the BCP. Okay, and you will see that as a result of plugging in these things will become 0 in C6, okay? Producing, forcing this to be 1, okay? Right, this literal to be 1. So if you look at C6, all these things which are called as see, all these will appear in negated form in C6, okay? And this literal itself will appear in positive form in X6, right? That's when it will be, all this, when you plug in, will have to be 0, and this will be 1, so and so forth. Okay, this itself will appear in negated form in C4 with these two, and this one will appear in positive form, okay? And so on, yeah? So if you look at C4 and C6, just any two clauses, the incoming and the outgoing, the clause that are labeled. So this particular literal will appear in positive form here in C6, in negative form, okay, as negation. Therefore, will be occurring in different polarities in this. Okay, that's another thing that you will have to keep in mind. So what is happening here? You see, it is making, it's kind of a cascade of implied decisions that you're getting. Okay, if you look at it from here, what happened was that as a result of these explicit decisions, there was a cascade of implied decisions that eventually got, when they got plugged into C2, it made it to be false. Okay, so here, and that itself was as a result of some x4 being 1, okay, and x1 being which was what caused x2 and x not of x3 to be 1, which resulted in this to be 0. Similarly, so in a way, all these things, okay, if you and that's how you get a cascade of decisions all the way going back to the explicit decisions. Okay, so these set of decisions are a no-no. These two, the one that make these three decisions, are also going to lead to this conflict, and so is this x1 and x4 and so on. So yeah, as a matter of fact, there was one other observation that you could make. You actually, in the implication graph, I'm keeping track, the way it was defined was I'm keeping track of these clauses, okay? Because of the two observations that I already made, you really don't need to see what those original clauses are. You can actually derive. For example, given this implication graph, you can actually tell what these clauses are. Can you guess? What should C1B? What should clause C1 be? Yeah, not of x1 or x2 plus x2, correct? Yeah. So that's how it is. So you could pretty much derive what the things are. C2 should be the negation of these two, this junction of the sum of negation of this and that, correct? C2, yes. X1, yeah, X1 not S, and so on. Okay. Of course, there is here. They can be. These were explicitions. If your original formula itself had some unit clauses which were unit, then they will not be result of exposition. Then the BCP right at level 0 itself would have kicked in. Okay, so you can also have this thing, and there are a couple of things. So So an antecedent of this one is defined as the clause. I mean, as the clause that is, that is clause that is labeled with the incoming edge. Okay, so that is what is called an antecedent. Okay, and yeah. So what does at one level? So based on the observation that I just now made, if you had the implication graph constructed, any by the way, this I've already defined. What is a conflict clause? It's implied by the original set of formula, and it blocked the partial assignments that led to the current conflict. Okay, that's what it is, and that's what you have to see what we can derive. So every cut of this implication graph is a conflict clause. Okay, recall what a cut is. So a cut is like a partition of your graph into two parts, so that they will completely partition into two disjoint set of nodes, and then the edge labels. I mean the predecessor. So for example, this is a cut because it completely separates the conflict side from the non-conflict side. Okay, if you cut it, these things, if you remove these edges, then this set of nodes will be, the graph that consists of that set of nodes will not be connected to this set at all. Okay? And a cut is defined as those nodes on the non-conflict side which have direct edges into the conflict side. Okay, so that's what cut is. Every cut that separates sources from the sink defines a valid conflict clause. Okay, so for example, there are lots of cuts here. Okay, I've shown 2 cuts, and I also have a slide which shows all the cuts. So this cut defines, will have these nodes, and the negation of that, okay, is a conflict clause. Because obviously the decision, the set of explicit decisions that you made, the negation of that will always prevent that, that conflict, okay? Now, the one that seemed attractive that we showed to be added, because that happens to be the shortest one, was produced by this cut of the implication graph. Because when you cut it here, what are the 2 nodes that have immediate edges from into the conflict side? It is X1 and X4. So the conflict clause corresponding to that cut of the implication graph is this. Okay, and as you can see, there are lots of other cuts, right? So give me one other cut. I'll give one very trivial one, and I will let you. So of course you could cut it here. Now, it'll give rise to 3. This also gives rise to 3. But when you cut it, what is the conflict clause produced by this? It is exactly C. I mean, it is C2 itself. Okay, so that you already know anyway, because C2 is there in the original form. There's nothing new to learn about it. Whereas these cuts, the other cuts, and are some new things that you have learned about your original thing. Yeah. That's right. So yeah, so you could, yeah, if you cut here, then this is the same as C2. But if you can have a cut like this, for example, here, if you cut something like this, that will have X1, X4, and X3. Okay, that's a new one. Okay, and you can also have something, then you can have something like this, and so on. Okay, so each of them will give rise to the thing. So let me have that. There was some question here from Sudakshina. Yeah, I know. I'm sorry, Sudakshina. I think I really don't know. I know that she does not. Some people are very adept, and I am a klutz, and I just do not. I don't know how to produce. Just okay. I figured out. So sorry, I didn't read your thing early on. So it take too much time to describe things. Already 6. Oh, that's a laser pointer. So I have to sit there. Yeah, okay. What? There are lots of cuts, but okay, yeah. So you see all the cuts here, okay, and each of them will have these clauses, okay. Now, there is this notion of something called a unique implication point, okay. What is a unique? This is a unique implication point. See, this occurs, this particular node occurs, I mean, every path from a source to this conflict node sink, okay, from the source which representing the decision at the current level, okay. These are earlier decisions made at earlier levels. So you see that X4 passes, I mean, every path from the decision made at the current level, which is what triggered this entire BCP, passes through X4. What is so special about X4? It's because you see that kind of covers all the other implied decisions following that. Okay, this kind of, it dominates. Okay, this is the notion of dominant node in a cut. Okay, so that's this, and such a thing is called a this one. Yeah, this one is a unique implication point. So that is a node in the implication graph through which every path from the decision, explicit decision made at the current level, from every path from that to the conflict node goes through. Okay, that is what this thing is. And any conflict clause cut that includes a unique implication point is good, because such a clause will have that unique implication point as the sole decision, implied decision made at the sole decision at the current level. If you look at all the other ones, they'll have multiple literals, okay? X2 and X3 here. This one will have, there's one here, which will have X6 and X5, okay? And so on. So besides being this being the one which has the unique implication point being the shortest one, that is one thing. But more importantly, since that is the only decision, once you add it and you backtrack, where, you know, keeping all the earlier decisions intact, it'll immediately flip this and force a right decision on X4. On the other hand, if you added things like this, or even further down here, okay, this one, of course, you know, after that, you will have two decisions at the current level, okay? So you still have to make a decision after that on these X6 and X7, and you may end up making a wrong decision, okay, and then hit into the same conflict. Whereas a clause which has the unique implication point, and that such a clause is called an asserting clause, okay? And it's because it's an asserting clause, because as soon as you backtrack by, you know, to an earlier level, yeah, so then you it forces a decision on that. So now the only exception is, you see this one which has you know, the one that you go all the way back is also has, I mean, this by definition is a unique implication point, because that itself is a source, and every path, you know, obviously every path from that, you know, is that node is on that, you know, that will, yeah, I mean, there also it has only that decision, okay, but it will not be the shortest one. Usually the unique implication point, a clause that contains unique implication point, the first unique implication point is one which is closest to your conflict side. That will be the shortest, because as you move further and further back into this, you will get, you know, longer and longer clauses. So in the beginning, you know, people used to add, SAT solvers used to add all the conflict clauses. The heck, I'll add all of them, okay? But of course, that will immediately, you know, so you will be adding lots and lots of clauses, and you are, the more clauses that you add, it's almost like going back to DPLL. What does DPLL do? I mean, just keeps on, you know, resolving and resolving, and then the thing. So, but most modern day SAT solvers will add Okay. Yeah, we'll add the one with the shortest, the first implication point. Okay, so that is one. And what else? Okay, the other one that I wanted to show, okay. So there is a way, of course, one way to derive obvious ways to maintain this implication graph and then compute cuts, okay? That's not a very efficient way to do, because even though this is only partial, you can see the BCP can be producing millions. I mean, just imagine there'll be millions of clauses with millions of literals in those clauses, and this implication graph can very huge. Okay, so the idea is not to find a way to construct these conflict clauses, to derive these conflict clauses without actually explicitly constructing this implication graph, and that's where resolution comes in handy. Okay. Notice what I observed earlier in the resolution. Okay. So first of all, C1 and C2 will have X2 in opposing polarity in that. Okay. So what does, if you resolve C1 and C2 on the pivot variable X2, okay, what do you get? Because what happened was, it is something that is implied by C1 and C2, okay? And if, since the negation of that will make, the negation of that will actually be this, the cut, okay? It will be the thing. So that will make it zero. So because this is something, C1 and C2, the resolvent of C1 and C2 will be something that is implied by C1 and C2. That means the negation of that will exactly be making this unit and C1 and C2 resulting false. Okay, and that's exactly what the assignment determined by the cut. Okay, therefore, if you see that you can derive each of these conflict clauses through a series of resolution steps. Okay, so series of resolution step going from the conflict node back. Okay, so you do C2 and C1. Okay, with this, then you get this cut. And after that, this was the next to last thing that was derived. You could then take the resolvent that you got in here, and then resolve it with C3 and so on. Okay, then you will get this then you will get this cut. Okay, and after that you do this, you will get the cut involving X1 and X4. Okay, so what you're repeatedly doing is you're starting with C1, C2, okay, and then you're resolving the result of this resolution with the antecedent clause of the literal. So you have to fix an order in which you derive these things, because there are places here where there are multiple things where you have to force an order, okay, and then you keep resolving that, and that's what is shown here. Okay. Okay, so for example, here, first I did C1 and C2, okay, resolved it to get the cut that you get shown here. And then you resolve that with C3, okay, which was this one. And then you get X1 and X4. After that, you get you go one step further and you resolve with C5, okay, and then you get X1, X4, and X6, and finally it ceases, and then you get this, and that's what is is the procedure. So there, what you need to do is you only need to keep track of not the implication graph, but point. This actually shows that this is exactly the code that is inside. Yeah, so you start with the clause that resulted in the final conflict being reduced to 0. So that's one. And then and then that is the initial clause. And then you take that is a C2, and that's the variable that you start with is X2, and you take the antecedent of that, okay, which is C1. And then you resolve it, which gives you this one, X. This is the resolvent. Okay. Then you will have to fix a certain order in which you actually you need to know the order in which you derived actually this thing, because when you have two choices, you could plug C5 first or C6. In this case, you have to plug. You could have chosen to derive this first or this first. Okay, so so that you'll have to fix. Now here, the order is a certain order which I haven't shown here, but that is the order in which you lose. And then and you keep doing this until you hit a conflict clause. Repeat until when? Okay, so it should be until you hit unique UIP. Where is that thing here? Repeat until one lit at the current level. Okay, so that's what this thing is. Yeah, and then you're done. But if you keep going, then you will enumerate all the cuts, and that's what okay. So yeah, and this is exactly what I had. So you will have to kind of fix. The implication order is there. Okay, it's only sometimes the graph itself doesn't show you, so where you will have to make an explicit choice in the way that you did. So given that, so you don't need to keep track of the things. So you just need to know all the order in which all the implied literals got derived, and then so you can go pick the antecedent and so on, and then you keep doing the resolution. Okay, and that's what this thing. So I think I'll have to leave right now. Okay, so maybe this is a good time to stop, otherwise the thing will launch. So still, there are, other than saying that there are two other points, and I will finish up, and they'll only take about 10 or 15 minutes, and that is, how do you decide? Okay, that's also an important thing. So we still have not talked about, there are plenty of choices that you get as to which variable that you pick to decide on. That influences greatly. That is mostly heuristics. There's no, if you could solve that, you would have solved efficiently, you would have solved the, SAT solving would not be NP complete, okay? The other thing is, a significant, almost 90% of the time of the effort of CDCL based SAT solving, you end up doing BCP, okay? So good engineering in order to make it efficient, the BCP is also an important thing. There, in order to do BCP, one of the big tasks that you have to do is to determine when a particular clause will become unit, okay? A very efficient way. I mean, just think about how you would do. You'll have to make scans over all the clauses every time a decision is made. If you have millions of clauses, that's not a very efficient way to do. But there was a patented algorithm, okay, which is what Z3 uses, that was invented at Princeton, and that is patented, and that is able to do it in constant time. So in the next class, to finish up, I will be discussing that, okay? The decision heuristic, it's simple. So there is one decision, I mean, that is patented, as well as the a constant time algorithm to decide when to determine when a particular clause becomes unit, okay? And those two are the thing, and what level to backtrack on. So those three things I will do, and then so okay.